Welcome back. Yes, previously we looked at Boolean algebra. We basically looked at De Morgan's theorems, the duality of De Morgan's theorems, and then we also looked at what? The Boolean laws. Basically, we went through all the Boolean laws. Now let's see how we can use Boolean algebra for simplification, both simplification and to basically work out what I will call sum of products and product of sums. This is basically working out expressions from truth tables. Let's have a truth table. I want to take a simple example so that something that we already know, so that we can predict what our outcome should be, so that we can see if our method works or doesn't. We have only two inputs, therefore 2 to the power of 2 is 4 combinations. That's the count 0 to 3. We've done this previously. You can look at our previous work. If you missed it, just go through some of our older videos and you will see how we get to these 4 combinations. 2 to the power of n, where n is the number of inputs. So we've got 2 inputs, 2 to the power of 2, 4. Now let's take an output Q, F, Z, whatever. Let's have F. And then let's say we take something as simple as an AND gate. Alright, so we know this is an AND gate. Only when A and B, if A and B are both high, do we get an output going high. So now let's look at this. Let's say, where do we get, which combination gives us an output? So our F is given there as what? As F is equal to, if I combine A and B. What have we done? We've used the truth table to just go straight to our output. It was only 1, 1, so it was easy. I will later call this the sum of products, or what we'll call the sum of mean terms. And you'll be like, how is this a sum of products? There's only one product. Yes, it's only because we've only got what? We only have one. Let me quickly perhaps look at AB as 0, 0, 0, 1, 1, 0, 1, 1. If I have an F here, which is 1, 0, 0, 1, certainly this is our equality comparator. If our A and B's are equal, if A is equal to B, then we have an output. That is the equality comparator, otherwise called the what? Otherwise called the exclusive NOR gate. So now let's see. I want to highlight that why I'm calling this the product, sum of products or sum of mean terms. Let's look at this here. This here is node A. If I combine node A with node B, I get an F, a high on F. If I combine also A and B, I also get a high. So we can say, okay, therefore F is given by node A, product with node B, or AND with node B, or I get a 1 there or there. So that will be A, B. We should know by now that this is the exclusive NOR gate. The output of the exclusive NOR gate. Remember, this is simply a exclusive O. I say A and I put an X. A exclusive O B not. Right. What I want to highlight here is that now we can see that's a product, and the O symbol is like a sum. So this is product 1, product 2, and this is a sum. So we've got a sum of products. It wasn't clear here. Why? Because we had only one output that was high, one combination that gave us a high. All right, so I think maybe it's clearer with the what? With the exclusive NOR gate. Now let's try and look at the alternative. I could argue that, but I can use the zeros also. Why? Because it means everywhere. If I follow our rule, this is not A combined with node B. If I combine these two, I get node F. I get not f. So meaning that if I oppose this, I'm gonna get what? I'm gonna get a 1 here. Alright. So I can treat the ones, if I invert the ones, I get what? I get I get a what call this a 0. Alright. If I invert the 0 in this case, I'll get a 1. So I could get ones by inverting this and obviously ordering these situations, meaning it's not sufficient to use the 1 and say that is conclusively not f. I'm just saying in this scenario here we get not f. We get not f there, we got not f there. What does it mean? It means that the other combination, which would be not a, b, and the other combination, which is a, not b, these combinations gave us a 0. But then now that would mean if I have not f, it's given by not a, yes, or that one, or the last one. So every instance that gave us a 0. So yes, now can I work out f from this? Obviously now, if I invert the one side, then I can safely mathematically invert the other side. That will be not a, not b, or not a, b, or a, not b. So what have I done? I have inverted the one side, I'm inverting the other side as well. Alright, what you do to on one side of the equal sign, you do to the other. So now, therefore it means double negation. I'm applying my rules now. Double negation falls away. So this here now I can break and say this will be, now I'm applying Boolean here. I'm applying what? De Morgan's theorem, sorry. I'm breaking that line. These two remain together, but that changes. But I'll also break that side of the line. That will also change. So that we've got something like this. So, what do we notice now? We can then say we've got a product. These are products. Let's break the lines further. What are we doing? We are applying what we call De Morgan's theorem. Break that line. Double negation falls away. Change that to, it was an end. Change it to an O. Break that one is going to be double lines as well, so it will fall away. So what we have is this. Then if you look at the next one, then break that line. It's going to be two lines on A, which will fall away. O, not B. Break that line. Not A, two lines on what? On B, it will fall away. And I have got something like this. So what do you see now? I have got, this is individually, that's a sum. That's another sum. That's the last sum. Oh, I said that's another sum. That's the last sum. If there had been more zeros, I was going to have what call this other theta sums. Now, if you look at these together, it's products. So this is a product of what? Of sums. Right. So we've got a product. So that's jumping the what? That's jumping the gun. Does it work out to this though? Let's work it out further. Therefore, with that product, what I need you to see is we could have gone straight here. Instead of doing this, we could have said, okay, this here is what? This here is, let's put a line there. In fact, let's join that line. Once we join that line, we change that sign. Now, when you change that sign there, it's going to be what? It's going to be O. It's going to take us there. All right. But I think I'm jumping the gun. Let's not jump the gun. Let's take it as it is now. Let's just take it as it is. I think it will be clearer. What I want to say is going to be clearer. if I do this, A or B, I want you to look at A or B here. We started off as a product. We had not A, not B. But as a sum, it's A is exact or is inverses. This is A, B. Now if you look at this here, what we've done is we've treated a 0 as a 1. We've treated a 0 as a 1. Where previously we said when it's 0 we are going to invert, this time when it's 0 we treat it as if it's a 1. We do not invert, we keep as is. Now we go to the other term. It was not A, B. So if this persists, we are going to see that this is going to be A. So where it was not A, it's A, but it's not a product, it's a sum. So if we change it to a sum, what changes is what? Where you treat the ones and zeros is opposite of what you do with the normal scenario, where a 1 normally reflects a what? As is, and the 0 is inverted. Now in this case here, you see now that this is what? A or not B. This not B was a 1, but they were saying not. A was a 0. Instead of saying not, we just kept it as A. So what I've been trying to explain here. So with the last one there, we say, there we go and say, not A. You can even look there. It's a 1, so we're going to treat it as what? As a 0, so it's not A. It's a 0, we're going to treat it as a 1, so this is what? O, B. So we could go straight up. Instead of going through this, we could say, no, if we are dealing with zeros, we are not going to do it like that. We are going to treat it as opposites. A, where previously it was supposed to be a product, is going to be a sum. As long as there's a 0, it's going to be sums. It's going to be sums. Where there's 0, it's going to be sums. But we treat this with the inverse of what they ought to be. This was supposed to be not A. The inverse of not A is A. This is not B, but not B. The inverse of it's going to be B. So all we've done is do the opposite of what we normally do. And then here, this is going to be A. The 1 is now the not. And then this is going to be A, not A, because it's a 1. And the B is going to be as is. All we've done is we've treated it different from what we do here. Here we've said 1 is what? Where the output is 1, we've said 1 stays as is, and what? And 0 is noted. Alright, is inverted. Now, so we look here, what does it do? If we go straight without having to go through the long process, we could go straight and say we've got our sums here, just get the product. So what do we do? There's the product. Let's clean it out and see if this is true. It must work out to the same. Let's go and say we need to expand this. Now we apply the rules. A times A is A. A times not B is, it was going to be not A, not B, but already there's a term in A. Alright, let me rather do it so that it's clear, because I might lose the following. Alright, so B is going to be, that one there is going to be A, B. That one there is going to be B, not B. In future, I will not do this. I want people to understand when I say, when the term is repeated, we know our rule. So I might as well not have wasted time writing it. I might as well not have written time writing it. We know this rule. So this one here is B, not B. That is 0. I might as well not have what? Written that. I could have only written the A. For that whole work, I could have written the A. But I dealt with these two. I still have the other one unscathed. So what I'll do now is I'll expand this. A, there's only A left here. A, that A, not A, is the same scenario as B, not B. It's a 0. So I'll leave it. Or maybe for the first example, let's do it. Which we know is a 0 or A, B. But that is what the only term that is left, and that's exactly what we got when you use the ones. So you see now, we could have used the 1 because there's fewer ones there. It would have taken us straight to the answer. So now how do you decide if you are not told? A clever person will go with the what? with what would give them lesser work to do. All right, but sometimes you are guided by the question. The question says give us this type. If they say do the sum of products, then you have no choice. You have to come and use zeros. Okay. If they say do product of sums, then you are going to what? You're going to come and do, oh, I said sum of products. You're going to come and look at the outputs that are ones. Sorry, I sort of spoke out of 10 there. Then if you are going to be asked for product of sums, sum of products sometimes called what? Sum of mean terms, you are going to use where your outputs are ones, okay, where your outputs are high. And then the product of sums, or what is sometimes called product of max terms, you're going to come and look at what? You're going to come and look at your outputs that where your outputs are zeros. All right. So only thing is you treat the what? You treat the highs and lows different. If your inputs are low for the sum of products, you treat them as inverted. And then if your highs, you treat them as you take them as they are. Now for a product of sums is the opposite. Now you see how we've taken the one way straight to it using one, because there was that remarkable scenario where we could just go at it once, but alternatively we could have taken the longer route, which is product of sums, and here it was proving to you that even though it's sum of products, it's actually derived. This product of sums is actually derived from the sum of products. Anyway, I started with the sum of products. All right, I just had to be careful that these were zeros. Therefore, this represented the what? The not output. But it ultimately culminates in this form, which is what I would call the shortcut method of it. You just go straight to that, to the sum of products. Let's go further and try that other example. Let's say we are happy with this one example here. Let me rather move it somewhere here, and then take the friend and say, but all that could have been simply done like that. We could have started there, or we could have started right there. Could have started straight up here. All right, here. So now I'm gonna take this one here. I'll go through the long process first. Let's say we already looked at how we got this from what? From the sum of products, or sum of mean terms. Now I'm gonna go and say, okay, AB. I already have that. I'm not gonna repeat that. It's a waste of space. I'm gonna go to where our outputs are zero. So here I'm gonna use product of sums. But I'll first prove to you that we get the product of sums from the sum of products anyway, because I could have taken it as it is and said not A. Remember, with product of sums, that would have been A. Okay, but for now, because I'm just proving it, for now I'm in the process of proof, so to understand how we got here. So this here would be B for that, or the other one A, B. Remember that if I went straight to product of sums, this would have been A, that would have been not, that would have been A, that would have been not B, that would have been not A, that would have been what? That would have been B, because the zeros are not inverted this time. So this here would have given us not F. But already you know that this is the exclusive OR gate. So if this is exclusive OR, let's say I wanted to make it a real shortcut, I would have said, therefore, not is going to be, in fact, before I do that, just to prove to what I mean here, I could have said not F is actually the exclusive OR gate, A, exclusive OR, B, which therefore implies that F, if I invert here, I have to invert there, so F is equal to A, exclusive OR, B, not. We already know that's the case, but this is me just trying to show you that some things we know where we're headed. We already know where we're headed, but we want to take it this way, where we say that the not F is equal to not A, B, or A, not B. But then now we say we don't want F, we want not F. So we're going to say what we do to one side, we do to the other side. So this falls away and becomes F. Now this is where we could have started. Now if you break our line there, not A, B, I've broken the top line, but that should change to from a what? From an O to A, and then this becomes A, not B, and the line is there. Now you can see it's product already, but we don't see the sum yet. Let's get to the sum. There it is. If we break the lines now, we can see it's not, which is going to fall away, or not B. And that's, if we break that one there, it's going to be not A, or not, which is just B. So you can see now we could have started our sum of product could have started here. We could have started our product of sums could have started here. All right, could have started right there. So we can head straight to the product of sums by simply using inverses. Where our 0 was not, we use the inverse of not, it becomes as is, it stays as is, ne? And then our B would have been it would have been B here because the high, but the inverse is going to be not B. So we could have just gone there and used inverses, and then we could have just done the product of sum straight. Now, and when we, just to prove, this here is going to work out to A, not A, that's a 0, A, not A, we're applying the law, that's a 0, or A, B, or not A, not B, or B, not B, which is another 0, B, not B, which is another 0. So we are left basically with the exclusive, the equality comparator. So now that will be, we know this is our equality comparator, which of course is the same as that. So that of course is our exclusive no. Point is, we could have started right here. So we could have gone straight there and said we are starting there instead. So this is us applying Boolean algebra. You can see that we had to apply Boolean here. We had to apply the laws of Boolean to eliminate those. So you really depend, and we're applying De Morgan's theorems here. So you need to see that we have been basically trying to show you where in the real world, the world of design, we need to what? To bring in our understanding of Boolean algebra. So hopefully that was a nice session. So I'll come back and show you how we can probably, I just did 2 easy examples. They can be longer, they can be bigger examples, but the gist is the same. The story just stays the same, it does not change. Stick to your understanding of Boolean algebra, stick to your understanding of what? Of De Morgan's theorems, and the rest will be as easy as peasy. Let's go and do a look at corner maps, but that will be our next session. So till we see you in the next sitting, enjoy yourselves. Ciao.